Okay. Hello. So I'll be presenting for Pedro and I for Distribution Theoretic Semantics for non-differentiable programming. Pedro already did one presentation today, so I'm doing the other one. But yeah, so the goal of this work is to solve two problems, both of them involving if statements. The first is the following. You can kind of represent the same function in many different ways using if statements in a way that breaks automatic differentiation. So like take this function here. It's effectively exactly the same as this function. It's just the identity function, except for this case at 0. And the problem is, what automatic differentiation, and like in practice, what it does is it goes down each branch for the conditional. So while the derivative of this is fine, it's just 1 everywhere. The derivative of this one, when you go down each branch, is 0 at 0. So this is unsound, because even though these are exactly the same function extensionally, the derivative of each one is different when we run down each branch, and that's bad. So that's unsound behavior. The other problem that we're hoping to solve with our work is that non-differentiability exists. When we try and differentiate a non-differentiable function, we end up with problems like Rayleigh's non-differentiable. There's like the Heaviside function. Anytime you have conditionals anywhere, you will generally break things. You'll generally break differentiability. And so the solution that we propose for this in this work that we hope to resolve these two problems with is distribution theory. And the general idea behind distribution theory is that instead of sampling at a point, you sample a neighborhood around a point. Oh, sorry. Let's just pick this up. So let's say we have this just nice parabola here. And we want to, instead of sampling at this point at 2, what the distribution will do is it'll take this weighted average around this bump and integrate these two functions together. And this bump, it's important that this bump has some nice properties. First is it has to be infinitely differentiable, and second, it has to have compact support. And so if we call this function f and we call this bump phi, then formally what we do is we just integrate them together. And that's how we take the weighted average around this point of this function. And this is how you can evaluate these things. Phi also, it's also important that phi is a pretty simple function, and then you can also change its magnitude, so its height and its radius, very easily. These are two constants in the closed form that you can just change. And so we call this formally, if we want to take a function and turn it into a distribution that takes these bump functions, which we'll call test functions, to distributions, we just lift the function f. So what can the function f be? F can be anything that's locally integrable. So it can have a lot of discontinuities. It can be broken up in a bunch of different places. It can be non-differentiable in many places, and you can still lift it to a distribution. And the important part about this is that, before we get to there, this is just another thing that we'll use notationally later. So this is just saying, if b is true, then evaluate f at that point. Otherwise, send it to 0. And so an example of this is just the Heaviside function. If it's less than 0, go 0. If it's greater than 0, go 1. And an important part about being able to lift all of these non-differentiable functions into distributions is that distributions are by definition infinitely differentiable. And so this identity up here gives us where this notion of differentiation comes from, in that for smooth functions f, differentiation here, this identity holds through a simple integration by parts argument. And so we can just define distributional differentiation more generally using this idea. So instead of taking the derivative of the distribution, you can instead take the derivative of the test function. And like I said earlier, the test function is always infinitely differentiable, so you can differentiate anything this way. And it will agree with your traditional notion of differentiation. And so if you want a more closed form, this is it. It's kind of ugly, but the general idea is at any point of discontinuity, you stick a Dirac impulse in there and multiply it by the magnitude of the discontinuity. And so we're onto our language now. This is basically just simply typed lambda calculus, except for 3 new types: pred, n, which is just the type of predicates for our conditionals that we mentioned earlier. drn, which is just our test functions, our bump functions, and d prime rn, which are our distributions. And like I said, the language is effectively just the simply typed lambda calculus, except with our distribution theoretic primitives. So just lift our conditional, differentiation, distribution application, and our bump function construction. And so there's some basic typing rules. This is just you're turning a distribution or a function to a distribution. We're taking our conditional, so taking your predicate and a function and turning it into a distribution using construction from earlier. This is differentiation. We can only differentiate, in this language, we can only differentiate distributions for technical reasons involving this semantic model behind this. For more details, come to our poster. And then this is just how you apply a distribution. You take a distribution, you take a test function, you just mash them together, and you get back a real number. So lastly, this is a simple example. This is the Heaviside function. When you differentiate it, this is what the differentiated program looks like in our language. You just, using the third line, or the third line of the differentiation slide from earlier, you just add a Dirac impulse there at of magnitude 1. And yeah.